Hello everyone. Today we'll be discussing about the two's complement representation, which is a part of Unit 3 in the advanced level curriculum. We'll be talking about both the representation as well as the arithmetic computations. First of all, we have to consider how the negative values are represented in binary in the computer. The usual way of representing a value in binary is that we simply take the place values and we generate the binary number. But the issue is, if you were to represent a signed value, say positive and negative numbers, we can't just simply put the sign in front of the binary value. This is not applicable when it comes to the computer, just being able to represent ones and zeros. So as a result, come up with three different methods. Number one is called the sign magnitude representation. Secondly, we have the ones complement representation. And today we'll be discussing about the two's complement representation. Complement representation. What we simply do is we consider the positive values to be the same. We don't do any manipulations. Say for example, if we have positive 23 to be represented, we just take the place values, and keep in mind in the A-level curriculum we are talking about a model computer that has 8-bit registers. So accordingly, if we put the ones and zeros in the correct place, we get such a binary number. You can see that here we have 16 as 1, and then 4, 2 and 1 being added up to 7. 7 plus 16 adds up to 23. So that is how we represent positive values in 2's complement. No manipulations at all. But if we consider negative values, for example, let's take negative 23. First of all, we need to find out the positive representation of this binary value. So we receive the same bit pattern as we did in the previous case, because we are considering the positive 23. The second step is to invert the bits, where the zeros are written as ones and the ones are written as zeros. And next step is to add a 1 to the least significant bit. The usual computational methods in binary addition is being used. So the inverted form is added by a 1, resulting in the 2's complement representation. Simply the inverted form of the number is known as the 1's complement, and when you add 1 to it, you get the 2's complement representation. One more thing that I would like to emphasize is that the most significant bit of the answer, or we can call it the leftmost bit. If the leftmost bit, or as the most significant bit, is a 1, we can determine that the value is a negative number, which should be the case in this matter. If the MSB is 1, the value that we have in 2's complement is negative, and if the MSB is 0, it implies that the value is a positive number. Let's try out these questions. To try and convert these values, we have 3 into the 2's complement representation. Another type of questions that we often get is to convert a 2's complement value into its decimal form. So in this matter, the first thing that we do consider is the most significant bit, which is the leftmost bit in a given bit sequence. So to explain that, if you consider an example of such a binary number, So the leftmost bit in this case is this 1, and that is actually known as the most significant bit, and the least significant bit would be the rightmost bit, which basically carries the lowest positional value. Now the most significant bit can be either a 0 or a 1. If it happens to be a 0, then we can say that the value that we are considering is positive. And to convert this into the decimal value, we can simply take the positional values and convert this binary sequence into decimal. If the most significant bit is a 1, that implies that the value represented by the 2's complement value is simply a negative number. So therefore what we do is we apply the 2's complement method into the given bit sequence and then convert that into decimal. Just to give you an example of both of these occasions, a bit sequence having the most significant being a 0. Since it is a 0, we know that it's a positive value. So what we do is simply take the place values and add the numbers or the place values of ones and find out what the value is. In this case, you can see the ones are representing the place values 32, 16, 2 and 1. So when you add all of them together, you get the positive value 51. If the most significant bit is a 1, so what we do is we know that it's a negative number, so we can't simply convert that into decimal. So rather what we do is apply the 2's complement method onto this again. So what we do is simply invert it and add a 1 to it, and by adding a 1 you get this value, and now you can actually take the place values to convert that into decimal, which gives us a negative answer 43. Let's try to practice this with a few examples. Now let's look at how the 2's complement arithmetic can be performed. In the first example, we have a positive value and a negative value. So to convert this into 2's complement, what we simply do is for the positive number, can simply take 45 and represent that in binary by using the place values. So keep in mind that we need to represent this in 8 bits to fit our registers. So it's 0 for 128, 0 for 64, 32 is 1, 0 for 16, 8 is 1, 4 is 1, 0 for 2 and 1 for 1. In the same way we can take negative 33 as well. Now even though we deal with negative 33, we have to first find out the positive representation of 33. So it's 0 for 128, 0 for 64, 1 for 32, 0, 0, 0, 0 and 1 for 1, which makes 32 plus 1 adds up to 33. And now we can convert that into the negative form using 2's complement. So first of all, we invert all the zeros into ones and ones into zeros. So we can invert it and add a 1 to that. which gives us this as the negative representation of 33. Now since we have found out both the values in 2's complement, we can simply add them. And negative 33 as well. And when you perform the computations, we can actually use uh, the computational methods in binary to do the calculation. So 1 plus 1 adds up to 2, so you can't represent 2 in binary. So what we do is you break it off into multiples of 2. So we have one multiple of 2 and the balance is 0. So you put the balance here and take the 1 over to the other side as a carry. So again 2, that makes it 0 and 1. Now this column adds up to a 3. 3 can be represented in binary as one multiple of 2 and the balance being 1 as well. Keep the 1 over here, take the 1 over to the other side as a carry. We again get 3, so it's 1 and 1. We get 2, that would be 0 and 1. Again 2, 0, 1, 0, 1, and 0, 1. Now you can notice that we have received 9 bits as our answer. Now the problem is within our computer we are only capable of representing 8 bits. So the additional 9th bit, or we call it the overflow bit, needs to be handled, and different methods handle it in different ways. In 2's complement, what we simply do is like we cancel it and consider only the remaining 8 bits. And also something that you can see here is that the most significant bit in this particular bit pattern is a 0, which indicates rather that the value here what we have in binary is a positive number. So since the value is positive, we can directly convert this into its decimal representation by taking the place values into consideration. So here we have an 8 and a 4, which adds up to 12, which is positive. So since you saw that the most significant bit is a 0, the answer is positive, we simply converted the received bit pattern into its decimal form. Let's take an example where both the values are negatives. You take negative 75 and convert that into binary. So we do not need 128, but we do need a 64. And from 64 to 75 there happens to be 11 more. So you don't need a 32 for that, you don't need a 16 for that, you do need an 8, you don't need a 4, a 2 and a 1 is required. So we have a positive representation of 75. So we'll apply 2's complement to get the negative answer. So first we'll invert the bits. And we will add 1 to it. Zero plus 1 becomes 1. So that is your negative 75. The same way we can find out the value, the binary representation of the negative 13 as well. 0 for 128, 0 for 64, 0 for 32, 0 for 16 as well, 1 for 8, 1 for 4, 0 for 2, and 1 for 1. That gives us positive 13. We'll apply 2's complement onto this again. So we have 1, right. After the inverting the bits, we can add 1 to this. Which gives us right. After converting both the values into negative 2's complement form, we can do the computation. So and we can have minus 13 as well. We can do the addition here. 1 plus 1 again is 2, as we did earlier. 2 is broken off into 1 multiple of 2 and the balance is 0. Put the 0 remainder, take the 1 out to the other side. 2 again 0 1, 2 again 0 1. There's only 1 here, so we'll put 1 that there. 2 again 0 and 1. 3 is again broken off into 1 multiple of 2 and the balance is also 1. Keep the 1 here, remainder, and take the multiple out to the other side. 2 again 0 1 makes it 3 1 and 1. So as we did earlier, we can actually cancel off the 9th bit since we are dealing with 2's complement. And you can see that after cancelling the 9th bit, the most significant bit that we receive happens to be a 1. If the MSB is a 1, we know that the answer is negative. And to find out the decimal representation of this, we need to first apply 2's complement onto this and then find out the place values to obtain the decimal answer. So if we do apply the 2's complement, first thing is we need to invert all the bits. So 1 becomes a 0, 0 becomes a 1. And we need to add 1 to this as well. 1 plus 1 is 0 and 1. 2 again 0 1. 2 again 0 1. And this 1 comes over. Right. So now since we have applied the 2's complement method onto the answer, we can take the place values to find out what this represents. This happens to be the place of 64. This would be 16 and 8, adding up to a total of 88. But since the answer was originally negative, we can consider this to be negative 88. Let's try out a few examples. The same exercises what we have been doing throughout the video. You can find it in the description below. If you have any other questions, please make sure that you comment it in the comment section, and please do subscribe to this channel. That'll sort of encourage me into creating some more videos. And if you do need for me to address to any other subject matter, please do comment them as well. So until next video, bye bye.